So either I can say if two heads is a one outcome, or I can say and one head. So like this, these three first three considered as an event. So an outcome or a combination of outcomes of a random experiment is called an event. For example, tossing of a coin is a random experiment and getting a head or tail is an event. Then we talk about the sample space. The sample space of a random experiment is a set of all possible outcomes of that experiment. For example, when a coin is tossed, the sample space S is this HT. H and T are the sample points of the sample space. So we collect all possible outcomes for any random experiment, and then we say that collection as a sample space, and any like this single outcome is known as the sample points. Like H is a sample point, T is a sample point. Then we talk about what is equally likely events. Two or more events are said to be equally likely. Two or more events are said to be equally likely if each one of them has equal chance of occurring. So if we have equal chance of occurring, then we say that these two events are equally likely. So for example, in tossing of a coin, the event of getting a head or event of getting a tail are equally likely. And if we are having unbiased coin, then we say that 1 by 2 is the probability of getting head and 1 by 2 is also the probability of getting tail. Now we talk about this mutually exclusive events. Two or more events are said to be mutually exclusive when the occurrence of any one event. Some of you, why there is a need of you people are again and again not giving your this Google Meet Gmail ID so that I am not getting disturbed by you again and again. For tomorrow onward, I will not allow anyone. I already given one Google form there and told you everyone to submit your details there and specify your email ID through which you are going to join this Google Meet class. Still, some people are not able to, or not yet they have filled this form, and then they are trying to join. Today I am allowing, from tomorrow onward I will not allow them. So now we are here in this two or more events are said to be mutually exclusive when the occurrence of one event excludes the occurrence of other events. It means this mutually exclusive events cannot occur simultaneously. For example, when tossing a coin, either head or tail will come up, but not both. Therefore, the occurrence of head is completely exclude the occurrence of the tail. Thus, getting head or tail in a tossing of a coin are mutually exclusive events. Then we have exhaustive events. Events are said to be exhaustive when their totality includes all possible outcomes of the random experiment. For example, when throwing a die, all possible outcomes are 1, 2, 3, 4, 5, 6. So, like if in this Dipanshu Thomas, hello, Mr. Dipanshu Thomas. Dipanshu Thomas, are you there? So here, this is you know that this one is your what we call, this one is the sample space when someone throw a die. Okay, either one, two, three, four, five, any one of them turn out. So if I say two events, one event is this one occurring of odd number, and another event is occurring of even number. So you can see these two events occurring of odd number or occurring of even number are the events in their totality, like their union. Their union is actually equal to this set, the sample space. So if we are having two events and their union is equal to the sample space, then we say that this and these events are exhaustive. Okay. So it means the pair of events or more than two events also are said to be exhaustive when their totality includes all possible outcomes. Now we talk about this complementary events. An event A occurs and the event A does not occur are called complementary events to each other. The event A does not occur is denoted by A this or A bar or A superscript C. The event and its complements are mutually exclusive. It means either A will occur or its complement occur, not both will occur. Now listen what happened. For example, in throwing a die, an event of getting odd number is this one, and the getting an even number is this one. So we are having two events. So if this is an event A, then its complement is 246, and we can see that both of them cannot occur simultaneously. Either one odd number is there or one even number is there. So these two events are mutually exclusive and also complement to each other. Then we have independent events. Events are said to be independent if the occurrence of one does not affect the others. In experiment tossing of a fair coin, the occurrence of the event head in the first toss is independent of the occurrence of the event head in the second toss and the subsequent tosses also. So such kind of events are called independent. That is occurring of one independent event is independent of the occurring of others. Then we come to the definition of probability. So there are two types of probability. They are mathematical and statistical. What you learned till now, mathematical and statistical, but both of them are not used in this modern era. So in this modern era, we are having another definition of probability. So first we see what is this mathematical probability, or sometimes we say it's a classical definition of probability or a priori probability. If the probability of an event can be calculated even before the actual happening of the event, that is, even before conducting the experiment, then it is called mathematical probability. So if the random experiment, you know that this one you know, like from your ninth or 10th standard, like if a random experiment result in an exhaustive, mutually exclusive and equally likely cases, out of which m are favorable to the occurrence of an event A, then the ratio m by n is called the probability of the occurrence of the event A and denoted by PA. And this thing you know, like total number of cases favorable to the event A divided by the total number of exhaustive cases. So this is actually known as classical definition of probability, and this probability is work only if the total number of cases are finite. Like some, like in tossing of a die, we are having six possibility. In tossing of a coin, we are having only two possibility. But there are some experiment where the number of total number of outcomes are infinite or sometimes uncountable also. So this definition of classical probability fails there. Another thing that this definition says that the events are mutually exclusive. It means the occurrence of one exclude the occurrence of other. So there are certain situations that we are not having this mutually exclusiveness, and then again this definition will not work. Then the third assumption of this definition is equally likely. Equally likely means that probability of getting 1 is also 1 by 6 and probability of getting 2 is also 1 by 6. Like, but if I am having some biased dice, in my biased dice, I am having the probability of getting 1 is 0.2 and probability of getting 2 is 0.3 and something is there. So in that case also this definition will not work. Then we have another definition of probability. So these are the cases I already talked about. The above definition of probability is widely used, but it cannot be applied under the following situation. If the if it is not possible to enumerate all possible outcomes of an experiment, if the sample points are not mutually independent, if the total number of outcomes is infinite, and if each and every outcome is not equally likely. Then we have another definition of probability that is known as statistical probability or a posteriori probability. If the probability of an event can be determined only after the actual happening of the event, then it is called statistical probability. If an event occurs m times out of n, its relative frequency is m by n. So in the limiting case, when n becomes sufficiently large, it corresponds to a number and which is called the probability of that event. So it means like I am tossing of a coin and head is coming and I counted that like out of 1,000 tosses and 600 times head is occurring. So the my probability is 6 by 10. But this is like here we are saying n is approaching to infinity. And we know that no one is going to throw dice or throw coin infinitely many times. It is not practical also. So here we get some approximation to the probability of occurring of head, but not the actual probability of occurring of head with this definition. Because in practical, no one is going to repeat the experiment or throw the dice or coin infinitely many times. So then we have this another definition that is now used in this modern era, and this is known as the axiomatic approach to the probability. On the basis of this definition of probability, we developed our all concepts, and this will definition of probability is able to handle all the problems are occurring with the other definitions. So what is the axioms of probability? Let here we assume that let S be a sample space and A be an event in S. So here we assume that what is the sample space and what we are having one event A also with us. And then we define a measure that one is not known as PA is the probability satisfying the following axioms. The probability of any event ranges from 0 to 1. So it means probability of A is greater than equal to 0 and less than 1. The probability of entire space is 1. Here we, instead of entire space we are saying the sample space. The probability of sample space is 1, that is probability of PS equals to 1. So and this one is known as certain event. It means this will definitely happen. If A1 and A2 is a sequence of mutually exclusive events in S, then probability of A1 union A2 union dot dot up to infinity is equals to probability of A1 plus probability of A2 plus probability of A3. So this is the definition or approach to the probability. On the basis of these three definitions, we developed our new probability theory. So here you know what is mutually exclusive. Mutually exclusive means A1 intersection A2 is empty. Even though they are pairwise disjoint. It means AI intersection AJ is empty and I is not equal to, for I not equal to J. Now some basics to the set theory related to probability, like here S is a sample space. In our notation we usually uh, denote capital S as a sample space. Then A bar is an event, it does not occur. Then A union A bar is always equal to the sample space, where A bar is a complementary complement to the A. Then A intersection B, it means A and B are mutually exclusive. Then A union B, that means event A occurs or B occurs, or both A and B occurs. A intersection B, both the events A and B occurs. So here you think this A and B are as an event. Now A bar intersection B are neither A occur nor B occur. A intersection B bar event A occur and B does not occur. A bar intersection B event A does not occur and B occurs. So this is the addition theorem on probability. So the statement is this: if there are two events A and A and B are mutually exclusive, and the probability of occurrence of either A or B is the sum of the individual probability of A and B. So here we have the one word, this mutually exclusive. Mutually exclusive means the A intersection B is empty. It means they cannot occur simultaneously. So we are having two events A and B such that they cannot their intersection is 5. And then we have to show that the probability of A union B, that is probability of occurring either A or B, is equal to probability of A plus probability of B. So you see the proof, like n be the total number of adjusted cases and equally likely cases of an experiment. Further, let M1 and M2 be the number of cases favorable to the happening of the event A and B respectively. Then we have this situation. PA equals to M1 upon N and PB equals to M2 upon N. And since the events A and B are mutually exclusive, the total number of ways in which the events A and B can happen is M1 plus M2. And this one is M1 plus M2 by N. And then this is the proof. And then when they are not mutually exclusive, then not mutually exclusive, it means A intersection B is not empty, it means there is something. So probability of A union B is equals to this. And probability of A is actually this one, and probability of B is by definition like number of this n A's, small n A representing the number of points favorable to A and divided by the total number of cases, that is ns. It means this ns, that is the number of elements, distinct elements present in the set S, and here S is the total sample space. And then this definition you will use. And then we can, you know this proof in your like from 10th and 12th standard, but we want to prove this with the help of axiomatic theory of probability. Where is that one? Actually, this proof like this theorem and this theorem, I don't want to prove this kind of theorem with this definition. Like this one is earlier definition of favorable number of cases and divided by total number of cases. And this proof I will not accept as a proof in exam also. If someone prove like this, I will get zero. Like I am not allowing also these Venn diagrams. If someone prove with the help of Venn diagrams, we will prove this theorem with the help of set theory, the axiomatic definition of probability. Okay.
तो मैंने बोला कि अभी रिप्लाई दे दीजिए, इसमें क्या है, हम खाली बाहर से वो दो ही कर देंगे।
तो किसको रिप्लाई देगा सर?
वो टिकिंग वाला देना है ना, किसी का एप्लीकेशन तो बिना रिप्लाई से रखना ठीक नहीं है ना।
हाँ,
ये हमारे पास मार्क्स का कोई फंड नहीं है एकेडमिक के लिए, पूरा खाली भर गया तो वो लिख के तो भेज दो ना। तो क्या करें, हम पैसा थोड़ा फी भर देंगे, अंकिती ले लेंगे और दोनों का 2000 ले लेंगे। इनको आधा घंटा का खाली टोक देने देंगे या बिना टोक से करेंगे, कोई जरूरी नहीं है टोक देने का।
ठीक है सर, अभी क्लास चल रहा है। ठीक है।
अरे बिना अपने सब कुछ करते हैं, पता नहीं क्या है जो नहीं हो रहा है, तो किसी भी एप्लीकेशन तो रिप्लाई तो करो ना।
ठीक है। So we will discuss some example. So this actually you already know this tossing of a fair coin. Like I'm using here fair word because till now you know the definition of this classical definition of probability, and in that definition you have always assumed your coin is fair. It means the probability of getting head and tail are 1/2, 1/2. But there are certain coins are such that their probability of getting head is zero point 0.4 and probability of getting tail is zero point 0.6. And for that kind of situation, we have developed this axiomatic approach to the probability. So we'll say here we are having this tossing of a fair coin. So here H is head, T is tail, and this S is your sample space containing all S and T, and here this is finite one. The events associated with the sample space are is this one, either S, because if we say either occur or tail will occur, we always say S occur. So S is the definite event. So this head and then this tail and then phi. And then we have another example of this one is like throwing of a fair die. Here we have 6 possible outcomes. There's 1, 2, 3, 4, 5, 6. And here the sample space is S. You have either 1 pair or 2 or 3, 4, 5. So these images like 2 is represented by this 2 and this 3 by 3. So outcome is 3 or 4, 4 dots, 5 dots or 6 dots. So the sample space containing the sample points 1, 2, 3, 4, 5, 6. Now we have one event, the event of getting an odd face, that is 1, 3, 5, and the event of getting 6 is this one. So this is the way we can generate the events. So what I told you earlier, that the subset. This is like this whole bracket, this whole circle is your sample space, and any subset of it is an event. Like this A subset of X is an event. So any subset of the sample space is an event. Then we have another example, tossing of a fair coin until a head is obtained. So we may have to toss the coin and any number of time before a head is obtained. Thus, the possible outcomes are HTH, TTH, and TTH like this. So, like in first toss, we will get head in second, or in third, or in fourth. So, like this, we have to go. So, how many outcomes are there? So, you can say there infinitely many outcomes are there. So, then that is the problem. Then, how you can divide by the total number of outcomes in this case? So thus the outcomes are countable but infinite in number. So the countably infinite sample space S is this one, H, T, H, T, T, H, T, 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 H, again T, T. So like this, we don't know no, where, up to when this head will occur. Another example is picking a real number at random between -1 and +1. The associated sample space S is this one, S such that S belongs to I, and S greater than equal to this small s is the actually outcome, and S below greater than equal to -1 and less than equal to 1, and the sample space is -1 to 1. So the event is picking a real number at random between -1 to 1. So you can pick anything like zero point 0.5, zero point 0.5 by 2, zero point 0.5 by 10, 0.5 by 100 or something you can pick, and all of them belongs here. And if you remember the last class, this is an interval -1 to 1. So it is actually uncountably infinite set. Okay. So there is another problem here. Actually, you say this in tossing of a coin, you have countably infinite points, but they are infinite, and now you are having uncountably infinite points. So how in this situation you use your this classical definition of probability, because you are not able to count the total number of outcomes in this case, although they are in uncountably infinite. Now another example is output of a radio receiver at any time. Suppose the output voltage of a radio receiver is any time t is the value lie between -5 to 5, and the associated sample space as is continuous is given by this. The probability of an event A is the number PA assigned to the event. So clearly this is also an uncountable space, uncountable sample space, and in this your definition, classical definition of probability will not work. This definition, this is a classical definition, that is NA representing the total number of events favored to A, and capital N is representing the total number of events, or total number of possible, like it's N, capital N is the cardinality, that is the number of distinct elements present in your sample space. So this definition will be called purpose like this: S is equal to this 1, 2, 3, 4, 5, 6 is this S, and A is the event this, and the probability of favorable cases for A is 1, that is NA, and the total cases are 6, and then PA is equals to 1 by 6. Now another is that if your coin toss twice, and what is the probability of getting two head, and you can see that in sample space for total outcomes, and for this A is only one possible, so it's 1 by 4. So here these are the like problem with the classical definition is limited to the random experiment which has only finite number of outcomes. In many experiments like above example, the sample space is finite. Each outcome may be assumed as equally likely. In such cases, the counting method cannot be used to compute the probability of events. But I have given you an example. If my coin is not biased, then this definition will not work. Consider the experiment of tossing of until head appears. As we have discussed earlier, there are countably infinite outcomes. So can you believe that all of them outcomes are equally likely? For example, there is the example. So like H, probability of H getting H, TH, or probability of getting TTH, or probability of TTTH, they are having different probabilities, so they are not equally likely. So that is another problem. Then we have this posterior definition, and that is this one: an experiment repeated n times under similar conditions, and event A occur n a time, and then we have this limiting definition, probability of A, this one. So suppose the example is die rolled 500 times, and the following table shows the frequency of each phase. Like 1 is occurring 82 times, so 2 is occurring 81, 3 is 88, like this we are getting. And we see that the relative frequency is close to 1 by 6, but they are not equal to 1 by 6. So how do we ascertain that these relative frequency will approach to 1 by 6? As we repeat the experiment infinite number of times. So, and you know that this is not possible. So this definition also inadequate from theoretical point of view because we cannot repeat an experiment infinite number of times. So how we ascertain that our ratio will converge all possible sequence of outcomes of the experiment. So these are the problems with this what we call this classical and statistical or posteriori probability. Now we have, I think, also visible. So sample space already discussed. Equally likely events already discussed. Mutually exclusive events. Yeah, this one is also statistical probability also. Axiomatic approach is also already discussed. Okay, in axiomatic approach, that third condition is this one: if A1, A2, AI are a sequence of mutually exclusive. So you have to remember this word in probability. What is mutually exclusive? It means they are pairwise disjoints. It means AI intersection AJ is empty when I not equals to J. Then the probability of their union is actually the sum of their probability. For example, in particular, if you have only two events A1 and A2, then the probability of A1 union A2 is probability of A1 plus probability of A2, and probability of A1 union A2 union A3 like this. And here I am assuming that this A1, A2, A3 are mutually exclusive. This part is also discussed. So now this is the theorem, na? That theorem. So we will prove this theorem we have discussed. Na? There in that PPT, that they have proved with the help of this classical approach, but I am not accepting that proof. I want this kind of proof on the basis of axiomatic theory of probability. So you, then I also mentioned like this: use axioms of probability, and you know that what are the three axioms of probability? These three: one, probability lies between 0 and 1, probability of sample space is 1, and probability of union of mutually exclusive events is equal to sum of their probability. So on the basis of these three, I have to prove this one. So first one is probability of A complement is equals to 1 minus probability of A. So first I have to prove this one. So how we will prove, you can see. You know that from the definition of complementary event that they are mutually exclusive. That means A complement intersection A is empty, and this A complement union A is the total sample space. So now we use, because these two are equal, this one is equals to this one. So if we apply probability to, because these two sets are same sets being equal, so the probability of this A complement union A is equal to probability of S. And this axiom says that this probability of S actually 1. Okay. So we are here. I have used the axioms definition, axiom 2. In axiom 2 says that probability of this sample space. This is exams 2. The probability of sample space is 1. Now, here you have already noted that this A complement and A having intersection 5. It means they are mutually exclusive. And here I am having probability of union of two events. One is this one, another one is this one. They are mutually exclusive. So now I use my axiom 3, because axiom 3 says that if you have two mutually exclusive events, this one and this one, then the probability of their union is actually the sum of their probability. So I used here the third axiom. And then I can write like this. Probability of A complement is equals to 1 minus probability of A. So this completes the first proof. Now we have second. Phi complement equals to S. So what do we have to prove? We have to prove the probability of empty event is 0. So we'll see how to prove this one. Phi complement is equals to S. And you know that the probability of phi complement is equals to probability of this, because this is a null event and its complement is equal to sample space, and these two are equal, then their probabilities are also equal. But here from the definition of or axiom 2, we know that PS equals to 1. So this is actually 1, and then you can write probability of phi complement is equals to 1. Now this probability of phi complement, we use the first proof, because this proof we have already proved. We have proved that if we have probability of any event A complement, then it can be equal to 1 minus probability of A. So here we are having phi instead of A. So it means 1 minus probability of phi. So I use the result 1 proved here only. Like this proved. Now we have proved this result here only. So I use this result for the event phi, and I will have this one. And then this one cancel out this one, and I will get the P of phi. That is the probability of empty event is 0. Now we have this third case. And third case is this one. The probability of event A is less than 1, where A is not equal to the sample space. So we will prove this, because in the first result we have proved that probability of A complement is equals to 1 minus probability of A, and then it can be written as probability of A equals to 1 minus probability of A complement, because this can be go to other side and this can come to that side. They can, this and this can change the side, and we will have this one. Now the axiom 1 says that the probability of any event is greater than or equal to 0. So if probability of any event, so A complement is also an event, so its probability is also greater than or equal to 0. So here I am subtracting a number from 1 which is greater than or equal to 0. It means probability of A is less than or equal to 1. Now we have fourth case. Fourth is this one. Probability of A minus B equals to probability of A minus A union B. Since our knowledge says that the A minus B, if you remember the definition of A minus B, it contains those elements of A which does not belongs to B. And A intersection B, it contains those elements which belongs to both A and B. So A intersection B contains both those elements which belongs to the set A and B as well. And A minus B contains only those elements which belongs to A only, but not belongs to B. So it means this set and this sets are nothing common as per their definition. A intersection B and this set are having nothing common. Then it means if I take intersection of these two sets, I will get empty event. And if the intersection of two events is empty, it means these two events are mutually exclusive. This event A minus B is mutually exclusive with event A intersection B. Now I check whether what is the union of these two events. A minus B contain those elements of A which does not belongs to B. So it means here we have excluded only those elements which are belonging to A and B as well in this A minus B. But we are taking union of A intersection B also. It means whatever elements we have skipped here, they are actually in this of A, they are actually here. In A intersection B. So the union of A minus B and A intersection B is actually A. Now this left hand
Sir,
side,
your
yes,
screen is not visual, sir.
I think it is visible.
Screen is not visible.
It is the same case with everyone.
No, sir.
Sudham Kumar, is it visible? Lakshmi Narayan, is it visible?
Yes, sir. Visible, sir.
So Rohit Kumar, I think there is some problem with your internet. You check and sort it out this one. No? So I am telling right now here that A minus B union intersection B is actually A and the probability of A because this left hand side equals to this right hand side. So what to say? It means that if this left hand side equal to this right hand side, it means the probability is also equal because this if two sets are equal or two events are equal. So I apply the probability measure to both sides of this equation, and I will get this one. Now this is A minus B, and this is A intersection B, and this one is union. And here in this statement, I am saying that these two events are mutually exclusive. Mutually exclusive, it means their intersection is phi, and it means that, and here I am taking union of two events. Such events, those are mutually exclusive. So I here now use my three axiom three, and the probability of this union is actually the sum of their probability. This is by axiom three. And then I can write like this because this PA can be taken at this side only, and this part I am taking to other side like here, and this completes the proof that the probability of A minus B is equals to probability of A minus A intersection B. Now we have this fifth part. This one, probability of A union B equals to probability of A plus probability of B minus probability of A intersection B. So from knowledge of set theory, we know that A union B contains elements of A as well as elements of B. Now A minus B contain those elements of A which does not belongs to B. It means if there are some elements common in A and B, that those elements are not in the set A minus B. But those common elements are belongs to this B. So if I take A minus B union B, I will get A union B. Because here we are considering elements of A and here I am considering elements of B and the common elements between A and B. And then this union will give us A union B. And again, if I check A intersection B, because A minus B contains those elements of B, those elements of A which does not belongs to B, so it means A minus A intersection with B is empty. And then I apply because this what do I say? These two events are equal. It means if I apply probability measure P to both sides of the events, I will get this one. And in this right side of the part, because these are two mutually exclusive events, I will use my axiom 3. I will get this one because the sum of the union of two mutually exclusive events is equal to the sum of their probabilities by axiom 3. And then this I have used proved in earlier result. This one probability of A minus B is like probability of A minus probability of A minus intersection B. So I will use this result here and substitute here, and I will get this. So this is the result I proved with the help of axioms of probability. So this kind of proof I'm expecting from you in the exam. So like if someone wrote the proof by using classical definition of probability, I will not give marks. Okay, because that proof is limited to if you are talking about the sample space with the cardinality finite. But I am expecting a general proof that is applicable for all kind of students. So this kind of proof I am expecting from you. If you write that one, that may be correct in a limited domain, but I will not give marks. So I think I have to stop here, and I have to take the attendance.